In fluid dynamics, we study about forces acting on fluid in motion. We study about Bernoulli's equation along a streamline and its analysis and its application to determine discharge by using Venturimeter, Orificemeter, nozzle meter, and to find velocity of flow using Pitot tube like that. And also vortex motion also there and the impulse momentum equation principle. So these are the some concepts behind fluid dynamics. Now let's see some important concepts by answering 10 questions. Let's get into it. The first question is, the momentum correction factor beta is accounted for. So why momentum correction factor is employed? So what is the reason? Option A, change in the direction of flow. Option B, non-uniform distribution of mass. Option C, change in total energy. Option D, change in mass rate of flow. So what is the reason to employ to account momentum correction factor? There are two factors, kinetic energy correction factor and the beta value. So why beta? Because of non-uniform distribution of mass. Option B is the correct one. Now let's see more about it and how beta is calculated. Momentum can be written as rho AV square into beta. So beta is the correction factor. We are accounting for momentum. So momentum formula is rho AV square, or we can say rho AV can be called as discharge Q. So rho Q into V. Rho Q can be called as mass flow rate. So rho into Q into V. So rho Q is nothing but mass flow rate, that is denoted by m dot. So this is the mass flow rate rho qv, that is nothing but rho a v square. And the momentum correction factor is given by this formula, beta is equal to 1 by a v square integration v square dA. So what is capital V represents mean velocity over total cross section area. So capital V represents mean velocity over total cross sectional area here, and small v represents the velocity over the elemental area, dA. So this is the formula for momentum correction factor, and beta value for uniform flow shall be 1 and turbulent flow in pipes shall be 1.2, and in case of laminar flow in pipes, beta is equal to 1.33. These are some typical values for momentum correction factor. And for the general velocity distribution given by this relation, v by vm is nothing but mean velocity, equals to 1 minus r by r naught per m. It means a general velocity distribution. For this general distribution, beta shall be found by using this formula, nothing but m plus 2 the whole square into m plus 1 divided by 4 into 2m plus 1. So this is a general condition for a general velocity distribution equation like this. And these are all about momentum correction factor. Now let's see kinetic energy correction factor, and it is given by using this formula 1 by AV cube integration V cube dA. What is capital V? This is the mean velocity. What is small v? Velocity of the elemental area dA. And alpha for ideal flow profile shall be 1.0 or 1. Turbulent flow in pipes shall be around 1.03 to 1.06, and in case of laminar flow it shall be 2, and in case of flow between parallel plates it shall be 1.543. These are some typical values for alpha. Here you can note one point. The alpha value for laminar flow is greater than that of turbulent flow because velocity gradient of laminar flow is greater than that of turbulent flow. Velocity gradient of laminar flow is greater than that of turbulent flow. That's why alpha value for, that is kinetic energy correction factor for laminar flow, that is 2, which is greater than that of turbulent flow, which is nothing but 1.03 to 1.06. Now let's move on to second question. The figure given shows the schematic diagram for measurement of velocity of air. So we are intended to measure the velocity of air, and the density of air is given as 1.2 kilogram per meter cube through a constant area of duct using a Pitot tube. A Pitot tube is employed so that we can find the velocity of fluid. Here the fluid is air. And a water tube manometer. The manometer is filled with water. The differential head of water is 10 mm. So differential head is given as 10 mm. What is the velocity of air? Option A, B, C, D. So we have to find the velocity of the fluid, that is nothing but in this case air, using Pitot's principle, basic principle of Pitot's tube. So the correct option is option C, 12.8 meter per second is the velocity of air in this case. Now let's see how it's calculated. V is equal to root 2 GH. This is the basic formula in the Pitot tube. And H, that is head, pressure head, is given by X into rho m divided by rho naught minus 1. What is rho m? Density of manometric fluid. What is rho naught? Density of flowing fluid. So X is the difference between the manometric head. This is the manometric head. X is equal to 10 mm in this case. So 10 mm into rho m divided by rho naught. What is rho m? Here manometric fluid is water. So 1000 kg per meter cube divided by rho naught. Here flowing fluid is air. So 1.2 minus 1. That gives the answer as H value, and we have to substitute that H in this formula, velocity formula, so that we get the velocity of air as 12.8 meter per second. So what if density of manometric fluid is less than density of flowing fluid? Then we have to adopt this formula, X into 1 minus rho m by rho naught. So this is the basic two formulas behind Pitot tube principle. Now let's see what is the exact principle for Pitot tube. Velocity of flow at particular point is reduced to 0. That means that point is known as stagnation point. Velocity is reduced to 0 means that point is called a stagnation point. The pressure there is increased due to conversion of kinetic energy. So what is kinetic energy? It's related to moving. First the water is flowing and it gets stopped at a point, so that the energy converted from kinetic energy to pressure energy. The increase in pressure energy at this point is used to find the velocity of flow. So how it is found? Using this formula. Velocity is equal to, that is V is equal to root 2 GH. This is the theoretical velocity, but in actual case there will be some loss. So to calculate or to accommodate some that loss, we are using coefficient of velocity, and CV shall be 0.98 for Pitot tube in general and 0.99 for Prandtl tube. For Prandtl tube, we are in case of Prandtl tube, we use the curved streamlines. In case of curved streamlines, Prandtl Pitot tube is used, and for that CV shall be 0.99. Why if you are using Prandtl tube? When the streamlines are curved, piezometric head at both the sections in a Pitot tube will not be same. So in that case, it is necessary to find out the piezometric head at same point at which velocity is to be measured, such that the difference of total head and also the piezometric head at the section in the beginning gives the velocity head. So this is the basic uh, reason behind using the Prandtl Pitot tube, and for that CV is 0.99. Now let's move on to the third question. For frictionless adiabatic flow of compressible fluid, the Bernoulli's equation is given by. So there are four options. Just give the correct relation for this scenario. Frictionless adiabatic flow of compressible fluid. Every word is important. So the correct answer is option B. This is the correct relation in case of frictionless adiabatic flow of compressible fluid. Compressible fluid. That means it cannot be a liquid. It can be air or something like that. Now let's see what is K value and what is why it is arrived like that. The compressible flow in an adiabatic process is given by using this formula, P by rho per K equal to a constant. So by using this fundamental equation, we get the Bernoulli's equation as this option B, K by K minus 1, P1 by W1. W is specific weight, or we can say rho 1 G. V1 square by 2G plus Z1. Z is the datum, V velocity head, here pressure head. So equals to K by K minus 1. It's for section 2, it's for section 1. That's it. That means K by K minus 1 P by rho G plus V square by 2G plus datum head remains constant. So this is the basic Bernoulli's equation for frictionless adiabatic flow of a compressible fluid, and for that we use this general equation P by rho per K equal to a constant. And what if Bernoulli's equation for steady incompressible flow that we frequently use in basic problems in fluid dynamics? This is the basic frequently used formula for Bernoulli's equation of steady incompressible flow. First is the pressure head, next is the velocity head or kinetic head, this is the datum head, and that equal to section 2, and there will be some head loss that is noted by HL. And what if flow is unsteady and compressible? Then the general formula goes like this: integration of dp by rho plus integration of dv by dt ds plus v square by 2 plus gz equal to a constant. So this is the general equation for unsteady compressible flow. So what are the basic assumptions in finding this formula? Bernoulli's equation for steady incompressible flow. So assumptions are steady incompressible inviscid, that means non-viscous fluid, and the flow happens in a streamline, and friction is absent, and only two forces are taken into account. What are those? Pressure force and gravity force. And velocity is said to be uniform. That should not be non-uniform velocity. So these are the major assumptions in arriving this steady incompressible flow Bernoulli's equation. So now let's see how Bernoulli's equation is arrived. What is the origin? First, Newton's equation. Newton's equation comprises of these many parameters. First one is the pressure force, viscous force, turbulent force, compressibility force, surface tension force. So gravity, pressure, viscosity, turbulence, compressibility, and the surface tension force. So these many forces are summing up that will give the Newton's equation. And what is the Reynolds equation? The summation of gravity force. Actually this is not A, this is G, gravity force. Oh, okay. So this is a gravity force. For Reynolds equation, it shall be summation of gravity, pressure, viscous and turbulent forces. That is nothing but we are neglecting compressibility force and surface tension force because we are assuming incompressibility. So that's why Fc is neglected, and surface tension force is very negligible in magnitude. So that's why F sigma is also neglected. In case of Navier-Stokes equation, we are also neglecting the turbulent force because we are uh, because we are calculating only for laminar flow conditions. So that's why Ft is also neglected. So Fg plus Fp plus Fv. And in case of Euler's equation, it shall be reduced to gravity and pressure force only because viscous force is also neglected. So this is the basic equation that is used to arrive the Bernoulli's equation. So gravity force plus pressure force, on deriving on making some derivations from this equation, we arrive the Bernoulli's equation. So now let's move on to fourth question. This question is based on pipe bend. A bend in pipeline conveying water gradually reduces from 30 centimeter square to 10 centimeter square and deflects the flow through an angle of 60°. So deflection is given and the diameters of two ends are also given. At the larger end, so this is the larger end, the gauge pressure is given as 180 kilonewton per meter square or kilopascal. When there is no flow, the horizontal component of the force, that is F suffix x, on the bend is, so this is the force we have to find in this case. So option A 600 Newton, option B 0, option C 320 Newton, option D 450 Newton. Here one concept is there, we use that concept to find the horizontal component of the force in case of pipe bends. The answer is option D 450 Newton. So let's see what is the concept behind it. Momentum, impulse momentum concept, impulse momentum conservation is the concept behind it. So when there is no flow, pressure at both the ends is same. So pressure at this end and this end shall be same when there is no flow, because they have given the condition no flow. And by applying momentum equation, so first in the section 1 and section 2, P1A1 minus P2A2 cos theta, y cos theta, we are making that as horizontal, minus Fx equals to rho q. Rho q is nothing but mass rate, mass flow rate into V2 cos theta. Here V2, here is the V2 value. V2 is making to horizontal, so that's why cos theta minus V1. So here flow is absent, so that's why this gets 0. This rho q into V2 cos theta minus V1 gets 0 because flow is not there. Velocity will be 0. So that's why only P1A1 minus P2A2 cos theta minus Fx equal to 0 will be there. So by substituting P1 value as 180 kilopascal and P2 also 180, because both ends are having same pressure because of no flow, and A1 is given by pi by 4 30 square. Actually they have given the area, not the diameter. So A1 is 30, A2 is 10. So P1 is 180 into 30 minus 180 into 10 into cos 60 equals to Fx. So by considering all the proper units, we get the answer for horizontal component of force as 450 Newton. Now let's see the general formula for both the directions. So this is a general formula: P1A1 cos theta 1 minus P2A2 cos theta 2 minus Fx equals to rho q into V2 cos theta 1 minus V1 cos theta 2. So this is the general formula for horizontal component of the force, denoted by Fx. And in case of y direction, so this is a y direction force. So what is the general equation? P1 A1 sin theta 1, here vertical, so that's why we are multiplying the trigonometric function sin theta plus P2 A2 sin theta 2 plus Fy minus W. What is that? Self weight of the pipe. So minus W equal to rho q into minus V2 sin theta 1 minus V1 sin theta 2. So this is the general formula for arrived by applying momentum equation. So these are the formulas to be remembered so that we can do any problems regarding pipe bends. Now let's move on to fifth question. Water flows up a tapered pipe. So flows up a tapered pipe. Find the magnitude and direction of deflection h. So this is the h of the differential mercury manometer corresponding to a discharge of 120 liter per second. Neglect the friction. So they have given the discharge value. We have to find the manometric head or the deflection of the differential manometer. Here mercury is the manometric fluid. So how to calculate that? By using Bernoulli's equation. Simple sum. So the H value is nothing but 17.5 centimeter. Now let's see how it's calculated by using Bernoulli's equation. At section 1, so the section 1 you can see here P1 by rho g, or we can denote that as gamma, or that is nothing but specific weight, plus x plus h equals to, this is at section 1, and we have to find pressure parameters for section 2. P2 by gamma plus 0.8. 0.8 is nothing but 80 centimeter between section 1 and section 2 data made, plus x plus sh. What is sh? This is the value of sh. You can see here the diagram. This is the sh. Actually this is h into we have to multiply s. So we can get this for rho gh. So pressure. S is the relative density of mercury. That is nothing but having specific gravity of 13.6. This is the general equation based on Bernoulli's theorem. Q equals to A into V. This is a basic continuity equation. A1 V1 equal to A2 V2. Here we know what is A1, 30 centimeter diameter they have given. So pi by 4 d square. V1 we don't, and equal to A2 into V2. So A2 is nothing but, here we can refer the diameter pi by 415 square into V2. So by substituting all those things and by using this Q value, we can find either V1 or V2. By finding V1 or V2, correspondingly we can find V2 or V1. So this is how we have to calculate using continuity equation to find the velocity at both the section as this. V1 equal to 1.6977 meter per second and the corresponding V2 as 6.79 meter per second. And Bernoulli's equation at 1 and 2 is given by this general formula. So by using this, we can get the answer for H. So how it is done? Here we can find P1 by gamma and minus P2 by gamma value. So we know V2 and V1. So we know V2, V1. P1 by gamma minus P2 by gamma we know from this equation. So all the parameters are known, only the h, small h parameter is not known. So by substituting all the things, we get the answer for h as 17.5 centimeter. That is nothing but the deflection of differential mercury manometer for the corresponding flow. Now let's move on to sixth question. A Venturimeter in an oil specific gravity is given as 0.8. So oil pipe is connected to a differential manometer in which the gauge liquid is mercury. So this is the gauge liquid and that is nothing but mercury here, and the flowing fluid is oil. So flowing fluid is oil. For the flow rate of 0.16 meter cube per second, the manometer registers a gauge differential of 20 centimeter. So this is the gauge differential that is given as 20 centimeter in this case. So this is the first scenario. An air oil manometer is connected to the same Venturimeter. So here the flowing fluid becomes what? Here the flowing fluid is oil, but manometric fluid becomes air. Manometric fluid becomes changed to air and is connected to the same Venturimeter. So then what is the new gauge differential for a flow rate of 0.08 meter cube per second for air oil manometer? So basic principle of Venturimeter is followed here to find the new gauge differential of difference so for a flow rate of 0.08 meter cube per second in case of air oil manometer. Option B is the correct one, 80 centimeter. Now let's see how it's calculated. So first we have to find the head of oil in the oil mercury Venturimeter. Oil mercury Venturimeter, we have to find the head of in terms of oil. So how to find that? H is given by x into rho m by rho naught minus 1. This formula is studied in the previous one of the previous questions. So here x is 0.20. How? They have given the differential. They have given the differential for oil mercury setup. So x is 0.20 meter. So rho m. Here manometric fluid in the first case it was mercury. So that's why 13,600 divided by rho naught, nothing but 800 minus 1. That gives the answer as 3.2 meter of oil. Now what is Q1 value? 0.16 meter cube per second. Q2 in the second scenario is 0.08 meter cube per second or Qmax. And for second scenario, what is the head in terms of oil? When we use manometric fluid as air, here manometric fluid is air, in this case x2. X2 is nothing but x2 is the one we have to find. X2 is the parameter we have to find. So here 1 minus rho m by rho naught. So rho m is what? Manometric fluid's density. So 1.2 divided by 800. So rho naught is the flowing fluid's density. Here flowing fluid is oil. So 1.2 divided by 800. So 1 minus that value into x2. So nothing but 0.9985 x2 meters. So 0.9985 x2 meters of oil. So by using the Venturimeter formula for discharge, we have to find we have to find x2 value. Here you can see the discharge for Venturimeter. Q is equal to CD, coefficient of discharge, into capital A, small a. Capital A for pipe, area of pipe, cross-sectional area of pipe. Small a is cross-sectional area of throat section, into root 2 GH divided by root of a square minus a square. Here, keeping all the parameters same in both the scenarios, that is CD, capital A, small a, and what else? All other things are same. Only the h, that is the head value, changes. So Q is proportional to root h. Then what is the relation? Q1 by Q2. Q1 by Q2 is equal to root of h1 divided by root of h2. We know what is h1. That is nothing but 3.2. H1 is 3.2 and H2 is 0.99 x2. So what is Q1? 0.16. What is Q2? 0.08. So all the things are known, only x2 is unknown. By using this relation, we can find the x2 in terms of air. So 80 centimeter of air is the differential, is the gauge differential for the second scenario. So this is the basic Venturimeter problem. So this is the basic discharge equation for Venturimeter. So what are the other devices to measure discharge? Orificemeter and nozzle meter. Now let's move on to seventh question. This is also a problem based on Venturimeter. Angle of diverging portion. So this is the diverging portion is limited to 7 degree. So what is the reason? Option A, flow decreases in diverging portion and pressure increases in downstream direction, so that adverse pressure gradient happens. If the diverging portion, that angle is large. If the angle is large, this will happen. Option B, if it is large, flow separation takes place. Negative pressure is created at the throat, which obstructs the flow if the angle is large. Option D, none of this. So what is the reasons behind it? There may be more than one options are correct. It is a MSQ type question, multiple select question. So be aware to select the options. Not only one option is correct. So the correct reasons are given in option A and B. Flow decreases in diverging portion and pressure increases in downstream direction. So it causes an adverse pressure gradient if the angle is large. So here converging portion, flow gets decreased, and as soon as the flow hits here, the flow gets decreases. Actually here is the contractile portion, and the flow decreases in the diverging portion. Here the flow is increased and the pressure increases in downstream direction, so causing the adverse pressure gradient if the angle is large. Flow separation takes place. This is regarding eddies. So you can see in this diagram, these are the eddy formation. So on the formation of this, so flow separation may take place if this angle is very large. So 5 degree to 7 degree is the optimum angle of divergence. So while in converging, 15 degree to 20 degree. Now let's see more about this Venturimeter. In convergent cone, flow is accelerating. We know why, because obvious reason is there, converging is there, so flow is accelerating. That means flow is increased, which may be allowed to take place rapidly in smaller length. So length of convergent curve is flow, convergent cone is very smaller, while in divergent cone retardation of flow occur. What is retardation? Decrease in flow. If that retardation takes place in smaller length, if this is happening in a very smaller length, then what happens? Flow separation may take place. So what is the another criteria? The length of the divergent portion shall be greater than greater when compared to convergent portion. Divergent portion is not at all used to calculate discharge. So that's why you can see here. This is the uh, manometer fitting path actually. So this manometer is not fitted over here, that is in the divergent portion. Only it is fitted in the convergent portion, before the convergent portion and at the throat. So that's why divergent portion is not used to calculate discharge. If cross-sectional area of throat is so much reduced such that pressure falls below vapor pressure, so pressure of flowing fluid falls below vapor pressure, then what happens? Cavitation. That is nothing but it is related to bubble. So this is the cavitation because of pressure falling below the vapor pressure of the flowing fluid. So these are some criteria behind the uh, convergent cone and divergent cone in Venturimeter. Now let's move on to eighth question. Eight questions based on vorticity. A right circular cylinder open at top is full of water like this. If it is rotated about vertical axis, so it is rotated about vertical axis at such a speed that half of the liquid spills out. So half of the liquid is spilled out. The pressure at the center of the bottom would be. Here we have to find the pressure at the center of the bottom. So option A, half of the original magnitude when it was full. Option B, 1 by 4th of the original magnitude when it was full. Option C, no change, unchanged. Option D, 0. So what will be the pressure at the center of the bottom after rotating in such a way that in such a speed that half of the liquid spills out? You can refer the diagram itself, you can get the answer. Option D, 0. So here you can see there is no point of pressure acting here. So that's why pressure at the center of the bottom is 0 in the final condition. Surface will touch the bottom at center. So actually the fluid surface is touching the bottom at center, so that pressure will be 0. So let's see more about the vortex flow. This is the fundamental equation of vortex flow. It's given by dP, change in pressure, is equal to rho v square by r dr minus rho g z. Basic fundamental equation for vortex flow. There are two types, forced vortex and free vortex. For free vortex flow, the basic formula is Vr is a constant. That is nothing but velocity is indirectly proportional to r. R is radius of rotation. Actually, this diagram is based on forced vortex, not a free vortex. Free vortex happens in a sink, whole sink like that. Free vortex. So for free vortex, Vr is equal to C. C is constant, and the circulation formula is given by this equation. Circulation is equal to 2 pi C, or 2 pi R into V. We can say like that. 2 pi C or 2 pi VR like that, and Z is equal to Z naught minus half of C square by GR square. So this is the basic equation for free vortex flow. And for forced vortex flow, there will be some speed. So that's why angular velocity is given omega r. So V is equal to omega r. Here you can notice velocity is directly proportional to radius of rotation. And z minus z naught. Z is nothing. Z naught are related to heights. This is the z naught you can see here, and z are related to heights. Z minus z naught is equal to v square by 2g. V is nothing but omega r, so omega square r square by 2g. And volume of paraboloid. So this is the paraboloid you can see here. Wait, I will erase all the things so that it will be clear. This is the paraboloid. This is the paraboloid formed uh, after rotating with some speed. So volume of paraboloid. This is the volume of paraboloid that will be equal to the volume of initial air. In this case, the water is filled up to its brim. In some cases, water will be filled up to here, and this is the volume of air. This is the volume of air. So volume of paraboloid shall be equal to volume of initial air present in the bucket or a beaker or something else. So that is given by this formula. Pi r square z by 2 is the volume of paraboloid and the volume of initial air. So consider this as a cylindrical beaker or like that. So for that, pi r square h is the volume. What is the h value? H is the height of initial air present before rotating. So this is the basic these are the basic things regarding vorticity and vortex flow. Now let's move on to ninth question. Ninth question is based on orifice meter. The coefficient of velocity of an orifice is given by what formula? You can refer this diagram to find what is x, to find the meaning of x and y. So option A or B or C or D to find the coefficient of velocity. Option A is the correct one. X by 2 root y h. So h is this one and x here and y here. You can visualize what is x, y and h. Now let's see more about it, how it is calculated. Using jet distance measurement method, is the coefficient of velocity is calculated as x by 2 root y h. And this CV value is defined as the ratio of actual velocity of jet at vena contracta. You can see here, this is the vena contracta region. This is the vena contracta region. So in that region, what is the velocity? So ratio of actual velocity of jet at vena contracta to the theoretical velocity gives the value of coefficient of velocity. And there is another term called coefficient of contraction. So coefficient of contraction is defined as the ratio of area of jet at vena contracta. So this is the area of jet at vena contracta in when it flows through a orifice plate. This is the orifice plate. You can see in this diagram clearly. This is the typical orifice plate. And what is the area of that vena contracta to the area of orifice? So to the area of orifice. So this is the coefficient of contraction. Here you can see the orifice plate in this diagram also. This is one type of orifice. This is one type of orifice. And there is another thing, coefficient of discharge. It shall be given by the product of coefficient of velocity and coefficient of contraction. And this CD value is a function of d by d. What is small d? Diameter at orifice. And what is capital D? Diameter of pipe. So these are some important points and important coefficients that are coming under orifice meter. Now let's move on to 10th question. 10th question is based on Venturimeter and it is inclined Venturimeter. A pipe carrying water has a 30 cross 15 centimeter square Venturimeter. What that means? 30 cross 15. 30 is the pipe dia, 15 is the throat dia. So the Venturimeter is inclined to 30 degree with respect to horizontal. The flow is upwards. The flow is upwards. CD value, that is coefficient of discharge value, is given as 0.98. Differential column height is given as 30 centimeter. That is nothing but 0.3 meter. Calculate the discharge. A simple calculation based on Venturimeter discharge formula. There is nothing to do with inclination. Just we have to calculate the discharge using the discharge formula for Venturimeter that we have already seen in one of the previous questions. So the answer is option A, 154 liter per second. Now let's see how it is calculated. So this is a basic formula to find the Venturimeter discharge. So CD is given, A, small a, all are known, H is also known. How H is known? By using this formula, del H is equal to X into Sm by S minus 1. This formula we have already seen 2 times in previous questions. Del H is equal to X. Here X is 0.3 meter into Sm. Here manometric fluid is mercury, so 13.6 divided by S. Here flowing fluid is water, so S is 1. So 13.6 divided by 1 minus 1 into 0.3. That gives answer as del H. So del H value is got and substitute here, and D2 is known, D1 is also known. Just substitute all the things in this formula. You can choose either this formula or this formula also. Both are correct to find your answer for discharge. And if they ask to find this del Z value, so how to find that? Z2 minus Z1. Here inclined to 30 degree. So we have to get it vertical. So that's why sine 30 degree. So 0.45 is the difference between this value. 0.45 into sine 30 degree. That gives the answer is 0.225 meter. And if they ask to find a pressure at the throat region by giving P1 value, for say example 50 kilopascal in the pipe section 1, we have to find P2 value. Then we can use this del Z value to find P2 value. So this is the purpose of inclination. This is the use of inclination actually in this scenario to find del Z. How to find the del Z? We have to make it vertical so that we can multiply 0.45 into sine 30 to get del Z as 0.225 meter. So by substituting this del Z in here, that is Z1 minus Z2, we can find the other pressure or throat pressure, while P1 is known and del H is also known by using this formula. So we are at the end of this video. If you like this video, please like, comment, share with your friends, and don't forget to subscribe the channel. Thank you for watching.